Hello everyone, in today's video we are going to discuss about pointwise and uniformly convergence. I have discussed this topic multiple of times and you will get all the links in the description. Today I have two questions of sequence of function and one by one we will check pointwise and uniform convergence. So our first question is f n t is equals to n plus 2 n plus 1 t to the power n 1 minus t for all t belongs to 0 comma 1. Okay, so pointwise convergence we will check whether the limit of this function sequence of function exists or not for all the points between in these intervals including the extreme points. For t is equals to 0, when we will put t 0, we can see that the magnitude of all the points belonging in this interval will be less than 1, as interval is from 0 to 1. Okay, and when we have mode less than 1 and we are approaching, let's say the magnitude of a is less than 1 and a to the power n, where this n is approaching towards infinity, it will approach towards 0. So our fx will be 0 for the points between 0 to 1. Let's check for 1. As we put t is equals to 1, this will be 0 and we will get 0 for 1. If we will put 0, so this t will be 0 and this will become 0. So we can conclude this that fx is equals to 0 for, as the variable is t, let's write this fnt is equals to, and here it will be ft. So this is 0 for all the points belonging from this interval. So this implies this is pointwise convergence. Okay, now in order to check uniformly convergence, we can use MN test, and MN test says that let's take supremum and limit n tends to infinity sequence of function minus ft, limit of the function. Okay, this is our ft, which is limit of this sequence of function. If this tends towards 0, as n is tending towards infinity, basically this is our mn, this value is our mn, and we say that if this mn approaches towards 0 as our n is approaching towards infinity, we say that our sequence of function is uniformly convergence. So in this particular case our ft is 0, so when we'll put the value of ft, we will simply get the mode of fnt. Now supremum limit n tends to infinity, our sequence of function is n plus 1 n plus 2 t to the power n 1 minus t. So let's check the extrema point of this function, and for that what we can do is we can differentiate this function one time. So d by dt of this n plus 1 n plus 2 t to the power n 1 minus t. I'm taking this as a constant, n plus 1 n plus 2 d by dt, and this will be t to the power n minus t to the power n plus 1. After differentiating, we will get n t to the power n minus n plus 1 t to the power n only n, and this will be as it is. This is first order differentiation of this function, and in order to get extrema point, we will equate it with 0. So this will be 0, only this function will be left, and this will be n into t to the power n is equals to n plus 1 t to the power, just a second, n minus 1, okay. So this will be n by n plus 1 t to the power n t to the power n t minus 1. This will get cancelled and I will get t is equals to 1 by n plus 1, which is less than 1. That means this point t is in the interval. Okay, so this is the extrema point. I'm putting this point in this function to check whether mn is tending towards 0 or not. So this will be n plus 1 n plus 2. Instead of t I can write n by n plus 1. As this n by n plus 1 is the extrema value, that means this function has extrema on this. So as n towards infinity, we are going to get n by n plus 1 as an extrema point. Then 1 minus n by n plus 1. This n plus 1 and this will get cancelled. This will be n plus 1, n plus 1 minus n, and n will get cancelled. And now we have n plus 2, n, and 1 by n plus 1. As you can see, this is limit n is tending towards infinity. We have this function, so we are just applying the limit now. As you can see, in the numerator we have n square and in the denominator we have n. You can write it as limit n tends to infinity n plus 2 by n plus 1. Okay, so as n tends to infinity, it will also tends toward infinity. We are not getting 0, so this implies that as we are not getting mn is approaching towards 0 or mn as a 0, we will say that this function is not uniformly convergent. Okay, so in first example it is pointwise convergence but not uniformly convergence in this particular interval. In the second example, first of all, let's check pointwise convergence. 1 by 1 plus n square x square. This is our fnx and the interval is from 0 to 1. Okay, when I will check on 0, this will be 0 and the function we will get 1 when we put x is equals to 0. This is fx. And when we will take any point, let's say a belonging from this interval, we will get this as 1 by n square and a square. As n tends to infinity, we will get 1 by infinity is equals to 0. So at any point between in this interval, we will get 0 when x is from 0 to 1. When x is equals to 1, in that case, this will be 1 by 1 plus n square. And as n is tending towards infinity, we will get 0. So I can put a close interval on this. So this implies that this is pointwise convergence. Pointwise convergence. As we are getting fx for all the points belonging in these intervals, in this interval. So this is pointwise convergence. But as you can see, this function is not continuous on 0. We are getting two different limits on 0. One when x is equals to 0, and between this interval our fx is 0. So we can clearly see that fx is not continuous at 0. Therefore we can imply that this is not uniformly convergence. Let's say if the question is on the interval, I'm taking some other interval, question is same, fnt, this is equals to 1 by 1 plus n square x square. Let's say if the question is on x belongs to a half comma 1. I'm not checking pointwise convergence here, because as we know that from 0 to 1 in this interval our fx is 0, so obviously this is a pointwise convergence. We get our fx as 0 in this interval. Simply we are checking uniformly convergence, so we need supremum, we need to check that supremum n tends to infinity fn x, this is x, fn x minus f of x, this should tends toward 0. So our fx is 0, this will be mod limit supremum 1 by 1 plus n square x square. So on differentiating we get 1 plus n square x square to the whole power square minus n square, this will be 2x. As you can see, this denominator is positive, 2n square is also positive, our x is from half to 1, this is also positive. This negative is making this first order derivative negative. So if this function is phi x, we are getting phi dash x is less than 0, which means this function is monotonically decreasing function. Decreasing, here we can imply this function is decreasing. So we will get minima at, as the interval is from half to 1, so as we are moving forward in this interval, this function is getting decreased, so we will get minima at half. When we will put this point in this function, we will get 1 plus n square, and instead of x I'm putting 1 by 2, this will be x square. And as this n will tend towards infinity, we will get 1 by infinity, this will tend towards 0, so this mn will tend towards 0. So we can say that although this function is not uniformly convergent in this interval, but it is uniformly convergent in this interval. Okay, so I hope you got the idea of checking pointwise and uniformly convergence, but if still there is any doubt, please let me know in the comment section. And yeah, one more thing, if anybody have a problem in the approach how we found the uniform convergence in first and second part, basically in first and second examples, I'm reshooting this additional part. Actually in first example, when we found the first order derivative and we equated it with 0 to get the extrema value, and as we got extrema, that n t value n by n plus 1, we saw that that value was less than 1 and that value was in between the interval. But in the second part, when we derivated it, its first order minus 2x minus 2n square x by 1 plus n square x square, so we found that that function is increasing or decreasing instead of equating it with 0. The reason was that when you will equate this with 0, you will get x is equals to 0, which does not belongs to the interval half to 1, and our motive was to find uniformly convergence in this interval. As we have already said that it is not uniformly convergence in this part, and 0 is a part of this interval, not this. So we were not getting the extrema of this particular interval. So we took a different approach. We found that whether this function is increasing or decreasing. If it is less than 0, it's decreasing. If it is greater than 0, it's increasing. So in this interval, the half will be the supremum. Half will give us the supremum value of the function, because this in this interval the function is decreasing. So that's why we took half. And okay, thank you.